All right, let's put on our detective hats. We're about to solve a fundamental chemical mystery that's happening all around us all the time.
Okay, so let's just dive right in. I mean, you know this, right? Some elements are super calm and stable, while others, well, they're basically explosive. But why? What's the real deep down chemical reason for this huge difference in, their personalities?
Just think about these two metals for a second. You've got sodium, which can literally catch fire and explode if it even touches water. And then you have gold. It's so unreactive you can wear it your entire life and it'll look exactly the same. So what gives? That's our mission today, to figure out why.
So, where do we start? Well, any good detective begins with the obvious stuff, right? The clues you can actually see and touch. So that's where we'll begin our investigation, with the physical properties.
First up is that classic shine. You know, the metallic luster? It's that bright reflective surface you get when a metal is pure. That's clue number one. It's something we all instantly recognize as metal.
Okay, next clue, malleability. This is just a fancy word for being able to beat a metal into a thin sheet without it shattering. It's the whole reason people could make stuff like gold leaf way back when.
And right alongside that, you've got ductility. It's kind of similar. It's the ability to be drawn out into a thin wire. I mean, just think about all the copper wires in, well, everything. That's ductility right there. And just to give you an idea of how wild this gets, check this out. Gold is so ductile that you can take just 1 single gram of it, that's about the weight of a paperclip, and stretch it into a wire that is 2 kilometers long. I mean, that is just incredible.
So, okay, a picture is starting to form here, right? Our metal suspects, they all seem to have things in common. They're shiny, you can shape them, they're usually hard, they're great at conducting heat and electricity, and they even make that ringing sound. Case closed? Ah, not so fast.
Because just when you think you've got it all figured out, the case throws a massive curveball. It turns out there are a bunch of elements that just completely break all the rules we just made.
So we have our nice, neat little checklist, don't we? Metals are hard solids, nonmetals are dull and brittle, and nonmetals are bad at conducting electricity. Simple.
But what about these guys? I mean, these categories seem so perfect until you run into the rebels of the periodic table. So how do we explain the ones that just don't fit into our neat little boxes?
This is where our whole case starts to fall apart. You've got mercury, a metal that's a liquid. Iodine, a nonmetal that's shiny. Diamond, which is just carbon, a nonmetal, is the hardest thing out there. And then you've got sodium, a metal so soft you can literally cut it with a knife. So yeah, our physical clues, they're clearly not enough. We have to dig deeper.
All right, to get to the bottom of this, we can't just look at our suspects anymore. It's time to put them in the interrogation room. We need to see how they actually behave when they react with other things. This is where we'll find the truth.
So we're going to put them through 3 big tests. We're going to see what happens when they meet air, when they meet water, and when they meet acids. This should reveal their true colors.
And right away, the first test shows a huge difference. You have metals like potassium and sodium. They're so reactive they just burst into flames in open air. That's why they have to be stored under oil. But then on the other end, you have gold and silver. They won't react with oxygen at all, not even if you heat them up.
Okay, the water test is even more revealing. You start to see a clear pecking order. You've got potassium, which just goes crazy in cold water. Then you've got magnesium. It needs the water to be hot before it'll do anything. And then there's iron, which won't even react with water unless it's steam. See the pattern?
So a really clear pattern is starting to pop out here. The metals that were super reactive with air, they're also the most reactive with water. And the ones that were totally chill in the air are the same ones that are stable in water. We're getting really, really close now.
Okay, this is it. It's time for the big reveal. All of our clues, from the crazy explosions to the elements that do absolutely nothing, they're all pointing to one single beautiful explanation.
So could there be one single list that puts all of this evidence together? A master list that finally cracks the case?
Yes, there is. And here it is, the reactivity series. This is our master key, the solution to the whole mystery. It's just a list that ranks metals from most reactive at the top, like potassium, all the way down to the least reactive at the bottom, like gold. And this one list, it explains everything we've seen.
But wait, a good detective doesn't just stop at what happened. They have to know why. So why does this series even exist? Why is potassium so reactive and gold isn't? Well, for that, we have to go deep inside the atom. And it all comes down to electrons. You see, it turns out that atoms are most stable, you could even say happy, when their outer electron shell is completely full. Think of the noble gases like neon. They're super stable and unreactive because their outer shells are already perfectly full. All the other elements, they're just reacting to try and get to that same happy, stable state. This explains it all perfectly. Just look at sodium. Its inner shells are full, but that outer shell has just one single lonely electron. The atom is absolutely desperate to get rid of that one electron. Why? Because if it does, its new outer shell will be full and stable. And that desperate need to lose an electron is what reactivity is. It's why sodium is so explosive.
So here's the bottom line. This one simple idea, this drive for a full outer shell of electrons, it doesn't just solve our little mystery, it explains so much more. It's why iron rusts. It's how a battery works. It's behind countless chemical reactions that shape our entire world. So it leaves you with a final question, right? What else in our world is secretly being governed by this invisible desire for stability?